Okay, so in the lecture today, we discussed this definition of the work in terms of this integral of the force. And if you remember this, the point of this is that if we have a situation where the force is not constant, then it varies as x varies, and therefore we need something more complicated than this very simple definition that we had for a constant force. And it's this definition of the work. So we need to integrate the force with respect to the position between some initial and final positions. And as an application of that, one of the things I mentioned in the lecture is we can do this for the work done by a spring force. So let's just imagine now a mass attached to a spring. As you can imagine, when the system is sitting at rest, so basically this is just sitting in its equilibrium position, and the mass sits at some point here, which we can call our zero, okay, which is the kind of equilibrium position. And if it's sitting there, then what that means is that there's zero force. If it's at rest, then the net force acting on this mass is zero, and therefore the force due to the spring must be zero. So here we would have Fs, the force of the spring, is zero. What about in this situation then? So we've pulled the mass to the right here. Okay, so again, this is our x variable here. We've pulled the mass to the right, and the spring has stretched out. Well, what's it want to do at this point then? So if we were to release the mass at this point, then it would shoot back over here, and that's because the spring is now applying a force in this direction. Okay, so it's actually pulling it wants to pull the mass back towards its equilibrium position. So in this instance, then the force of the spring would be negative because it's acting in this negative x direction. And conversely, if we were to squeeze the spring, so if we were to press the mass in towards the kind of base of the spring here, and we're compressing it, then this now is sort of exerting a force back towards the equilibrium position. So now our spring force would be greater than zero. It's positive. Okay, so really the point of this now is that the force always will point towards the center. So when it's at the center, the force is zero. When x is positive, the force is negative. When x is negative, as in the mass is over here, kind of before zero or at a position less than zero, then the force is positive. Okay, and this is encapsulated in what's called Hooke's law, which some of you might have seen before. Hooke's law says that the force is approximately proportional. Pen is set too thick there. Is approximately proportional to the position. Okay, and in fact, we have Hooke's law as a formula. So we have the force due to the spring is equal to minus k times the displacement. Okay, so here, if our displacement is zero, then the force will be zero. If the displacement is positive, then this negative sign here will make us have a negative force. And if the displacement is negative, then that cancels with this minus sign here, and we end up with a positive force as necessary. So this is for in 3 dimensions, but in 1D, just to say, in 1D, the more familiar form of this is Fs of x is equal to minus k times x. Okay. Now, what is k? K is what's called the spring constant. And basically, k is based on the material properties of the spring. So if I have a particularly rigid spring that really wants to get back to its equilibrium position, then k will be very large, i.e. the force will be very large. If the spring is a little bit looser, then k will be correspondingly looser. But it's based on basically the material properties of the spring. Just to say, this is measured in, what will the units be? Well, it's force here, so that'll be measured in newtons. This position or displacement is measured in meters. So the units of k here must be newtons per meter. Now, we will actually describe the dynamics of this system and under other kind of more realistic conditions where you have resisting forces and so on in a later chapter. Okay, so in later weeks, we'll actually get to this in the lectures. But for now, we're just considering this from a work energy point of view. Okay, so let's think about what the work done by the force due to the spring is. Okay, so using the previous result. Okay, what is the work done? The work done by the spring is going to be the integral between whatever our initial position is and whatever our final position is of the force due to the spring, which is a function of x, integrated with respect to x. So all we've done here is write down the definition of the work, but we're now using specifically the work done by the spring and the force done by the spring. Now, we know what the force done by the spring is. It's given by this expression, minus kx. So this will give us minus k. That's just constant, so we can take that outside. Integral between minus between xi and xf of x dx. So that's just substituting in minus kx in place of this fs of x, which is what we have here. Okay, and we know how to do this integral. It's just the integral of a sort of polynomial term. When we do this integral, we get minus k. We're going to get a factor of a half from here. Okay, so this will become x squared over 2. So I get minus k over 2. And it's going to be x squared evaluated between xf and xi. So this just becomes minus k over 2 xf squared minus xi squared. Okay, so clearly, again, we've got an expression for the work done by the spring, which depends only on the initial and final position. So what that means is it doesn't matter what path we take to get between these initial and final positions, okay? So I could, for instance, start at the equilibrium position and press the spring in and have it go back and forth a few times and then finish at some final position. Or, of course, I could do that much more quickly. It doesn't actually matter. The work done only depends on the position. It doesn't depend on the path taken to get there or on the velocity, okay? So just note that this work depends only on initial and final positions. Okay. Also, let's think about whether the work done is positive or negative. So if I end up at some final position which is larger than my initial position, and bear in mind that this could mean because these are squared, it doesn't matter if I'm on the left-hand side of the equilibrium position or the right-hand side of the equilibrium position. If my net distance away from the equilibrium position is larger in the end, then this bracketed term here will be positive, and I end up with a negative value for the total work done. Okay, so if the magnitude of xf is larger than the magnitude of xi, then that means that the work done is positive. Sorry, opposite of what I just said. The work done is negative. So this bracketed term is positive, so the whole right-hand side is negative. So if xf is larger than xi, then the work done is negative. And what this means is the block gets further away. From equilibrium. And if you think about this, a little similar to what we did with gravity. Okay, remember that we said if the work done by gravity is negative, what this means is the change in kinetic energy is negative. And that means that we're kind of taking kinetic energy out of the system. So we're actually reducing the velocity or reducing the energy. And that's the case here. If I move the particle further away from the center, the kinetic energy actually goes down because the spring is kind of resisting it more and more and more. So work done is negative if I get further away. On the flip side, if xf is less than xi, so if I move closer to the center or to the equilibrium position, then the work done by the spring is positive. So the block gets closer to the equilibrium position. Okay, and this is kind of really important to remember. So the kind of relationship between work and energy helps us to understand the dynamics. So we will reference this when we actually describe the dynamics of this spring system later. But this is an application of the theory that we discussed in the lecture today, where we're using our definition of the work done in terms of this integral to actually calculate the work and thereby the energy of our spring system.